Hello, and welcome to Science with Mr. Morgan. In today's episode, we're going to talk about chemical interactions. To start, we're going to look at bonds. Bonds as in James Bond? Nah, chemical bonds. A chemical bond is the force of attraction between atoms or ions, and these form when atoms share or transfer valence electrons. So what is the goal of chemical bonds forming? Ultimately, it's to achieve a full outer energy level, which is the most stable arrangement. Now, there are different kinds of chemical bonds that can occur to get to this arrangement. First up, we're going to talk about covalent bonds. These are bonds that form from the force of attraction that holds together two atoms that share a pair of valence electrons. These bonds may form between the same element or different elements. There are two subcategories of covalent bonds. We have polar covalent bonds and nonpolar covalent bonds. Polar covalent bonds occur when electrons are not shared equally between the elements. This leads to one atom being slightly negative in charge, while the other is slightly positive in charge. Nonpolar covalent bonds occur when electrons are shared equally, however, which is opposite of the polar. And because of the equal sharing, both atoms remain neutral in charge. Well, that's enough about covalent bonds. Next, let's look at ionic bonds. These bonds form from the force of attraction that holds together positive and negative ions. Specifically, these form when atoms of a metallic element give up electrons to atoms of a nonmetallic element. Basically speaking, metallic elements want to give up electrons, while nonmetals want to gain electrons. While ionic bonds form from metals and nonmetals, metallic bonds form between positive metal ions and the valence electrons that are constantly moving around them. Within these, the ions form a lattice-like structure held together by the metallic bonds. And this lattice-like structure explains why metals can conduct electricity and bend without breaking. Now, the last type of bond that we're going to look at today are hydrogen bonds. As the name suggests, hydrogen bonds involve hydrogen. These form from the force of attraction between the partial positive charge of hydrogen atoms of one molecule and the partial negative charge of an atom of a nearby molecule. Now, only certain elements have the potential to bond with hydrogen. Some common examples of these include fluorine, nitrogen, and oxygen. And for the intent of this lesson, these bonds are relatively weak. Anyway, let's revisit compounds, which we talked about in the chemical properties of matter episode. Can someone remind me what a compound is? That's right. It is a unique substance that forms when two or more elements combine chemically. Now, compounds always consist of the same elements in the same ratio, and they are made up of atoms that are held together by different bonds. Covalent compounds consist of atoms that are held together by covalent bonds, and these exist as individual molecules and are made up of non-metals. One very common example that you're familiar with is water. 2 hydrogen atoms and 1 oxygen atom. Ionic compounds, however, consist of ions that are held together by ionic bonds. And these exist as a matrix of many ions, aka crystals. These are made of metals and nonmetals. One very common example is sodium chloride, aka table salt. 1 sodium atom with 1 chlorine atom. In the chemical properties of matter episode I mentioned earlier, we also touched on reactivity. Remember that reactivity is just the ability of an element or compound to react. So, we've talked a little bit about this, but what is a chemical reaction? It is the process in which some substances, aka reactants, change into different substances, aka products. During the reaction, chemical bonds break in the reactants and new chemical bonds form in the products. Now, more specifically, what are reactants? These are just substances that start a chemical reaction. So if those are reactants, then what are products? Products are the substances that are produced in the reaction or from the reaction. Now, remember the law of conservation of mass that states that matter cannot be created or destroyed? That applies here. Reactants and products contain the same atoms, but those atoms get rearranged during the reaction. And due to this, reactants and products are typically different substances. Sometimes chemical reactions are irreversible, which means that once it happens, it can't go back. And these reactions are where reactants can change to the products, but the products cannot change back to the reactants. Another way of saying the same thing. Sometimes chemical reactions, however, are reversible. These reactions are where reactants can change to the products and the products can change back to the reactants. Somewhat of a back and forth at times. Under certain conditions anyway. Chemical equations, aka the formula for chemical reactions, must be balanced because matter cannot be created or destroyed in chemical reactions. Now, just like there being different types of bonds, there are different types of chemical reactions. First up, let's take a look at synthesis reactions. These occur when two or more reactants combine to form one single product. And this is represented with a capital A plus a capital B goes to capital A, capital B. A specific example is 2Na, aka sodium, plus Cl2, aka chloride, becomes 2NaCl, aka sodium chloride or table salt. But that's synthesis reactions. Next, let's look at decomposition reactions. These occur when one reactant breaks down into two or more products. And this is represented with capital A, capital B going to capital A plus capital B. Examples of this include the breakdown of hydrogen peroxide to water and oxygen, or water to hydrogen and oxygen. The next kind we're going to talk about are replacement reactions. And these occur when elements switch places in compounds. Now, these reactions typically involve ions. Now, I say typically, it's not always. In these reactions, generally more reactive elements replace less reactive elements. And there are subcategories of replacement reactions as well. You have single or double. Single replacement reactions occur when one element replaces another element in one compound. And this is represented with capital A plus capital B, capital C going to capital B plus capital A, capital C. Double replacement reactions occur when two ionic compounds exchange ions, producing two new ionic compounds. And this is represented with capital A, capital B plus capital C, capital D goes to capital A, capital D plus capital B, capital C. They just swap places. Hence, replacement reaction. Now, following this, let's look at combustion reactions, another type. These occur when a fuel reacts quickly with oxygen, O2, and produces carbon dioxide, CO2, and water, H2O. The general equation of combustion reactions equals fuel plus O2 goes to CO2 plus H2O. And the fuel that burns usually consists of hydrocarbons. So what are hydrocarbons? Well, one hydrocarbon example that you may have heard of is methane, CH4. All hydrocarbons are carbons with hydrogen atoms attached. In association with combustion reactions, there are exothermic reactions as well. And this is a category of chemical reactions where less energy is needed to break bonds in the reactants than is released when new bonds form in the products. And because of this, energy is given off. Now, this is often given off in the form of heat, which causes it to feel warm. Now, when you hear or see exo, think out. Exothermic reactions send heat out. All combustion reactions are exothermic. And if you've ever heard of an experiment called elephant toothpaste, this is a very common exothermic reaction. Now, opposite of exothermic reactions, there are endothermic reactions. And this is a category of chemical reactions where more energy is needed to break bonds in the reactants than is released when new bonds form in the products. Now, because of this, energy is taken in. And this is often in the form of heat again, which causes endothermic reactions to feel cold. Now, when you hear or see endo, think in. Endo, in. Endothermic reactions send heat in. And one of the most important series of endothermic reactions is photosynthesis. So instead of heat for these, energy comes from light. Specifically, most photosynthesis involves sunlight, at least outside. Now, with each type of chemical reaction, there are different components that make up chemical reactions. First, let's look at activation energy. This is the total amount of energy needed to get a chemical reaction started. It is necessary for reactants to move together, overcome the forces of repulsion, and start breaking bonds. So it's a very important form of energy, or type of energy, I should say. Next is the reaction rate. The reaction rate is just how fast or how slow a chemical reaction occurs. Factors that can affect the rate include, but are not limited to, temperature, concentration of the reactants, surface area of the reactants, or presence of a catalyst. But Mr. Morgan, what is a catalyst? A catalyst is a substance that increases the rate of a chemical reaction. It increases the rate of a chemical reaction by providing an alternative pathway for the reaction that has a lower activation energy. You can think of catalysts similar to a bridge. Without the bridge, you'd have to travel farther to get to your destination, to go to a different bridge. But if there is a bridge closer to you and you take it, it's less time, less energy, less activation energy to get to your destination. So catalysts just bridge the gap and make it easier or faster for reactions to occur. Catalysts, again, lower the activation energy that's required for the reaction to occur. And a lower activation energy means more reactant particles have enough energy to react, which means a faster reaction time. Now, catalysts in living things like you or I are called enzymes. And that brings us to the end of today's lesson. Until next time.